The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, we talked about this a little bit last time. We were talking about the detection of vectors in a white Gaussian noise. When we talk about vectors, we'll often refer to white Gaussian noise as noise where each component of the vector is independent of each other when they're all the same variance. Usually we take the variance to be n0 over 2, capital N0 over 2. And we'll say more about that as we go on, but that's just, I guess one thing I ought to say about it now. People keep wondering why we call this N0 over 2 instead of something else. And as I said before, there's really no reason for it except custom. The one important thing that you can always remember, and which is always true, is that anytime you're talking about a sequence of real noise variables, they all have variance n0 over 2 in the same coordinate system that you're using to measure the signals. Okay, the only thing that ever appears in any of these formulas is a ratio of signal power or signal energy to noise signal power. And if we're up at passband, we're dealing with the power which is 2 times larger than that at baseband. And because of that, and this is what really gets confusing, is that when you talk about n0 over 2 at passband, you are talking about something which is twice as big as the n0 over 2, the same n0 over 2 you were talking about at baseband. And the reason is, since the signal is twice as big there, the noise is also said to be twice as big. I can't do anything about that. It's just the way that everybody does things. The other thing that everybody does, since everyone gets confused about that, is after they get all done dealing with anything in a paper they're writing or something, they always look at the signal-to-noise ratio that they have, and they remove all the factors of 2 that they know shouldn't be there, so that you shouldn't trust anything in the literature too much as far as factors of 2 are concerned. And I try to be careful in the notes about that, but you shouldn't trust the notes too far along those lines either. So eventually I'll get the notes straightened out on all of that, but I think they're pretty close now. But anyway, we were looking at this question of how do you detect antipodal vectors in white Gaussian noise. And the picture that we can draw is this. Namely, we have 2 signals. One is the vector A, one is the vector minus A. It's in some finite dimensional system, but we're viewing it as far as drawing a picture as a 2-dimensional system. So A has some arbitrary component in the first direction, some arbitrary component in the second direction. Minus A is, of course, the reverse of that. This point right in here is the 0 point, which is halfway in between them. And the output that we observe is either plus or minus A plus this independent zero mean noise Z, which has the kind of circular symmetry indicated here with these little circles. Each of the Z sub i's have the same variance. They're independent of each other. And when you write down the likelihood of the probability density of this output, given that the hypothesis was 0, namely that plus A was the signal which was chosen. Okay, remember, in all of these things, there's this process now going on that we usually don't talk about anymore. But there's an input coming into the communication channel, which we're now calling capital H. It's the hypothesis, which is the thing you're trying to detect when you're all done. That input, which is 1 up to capital M, or sometimes 0 up to capital M minus 1, is then mapped into a signal from a signal set of capital M different signals. So there are m possible signals in this signal alphabet. You map the hypothesis into one of those. From those, you generally form a waveform. This waveform might be modulated up to high frequency, back to low frequency again, detected or whatever. You get some vector v at that point, which is a sequence of samples that you're going to be taking as far as most cases are concerned. And we'll talk more about that later today. But anyway, v is a vector, which is plus or minus a at this point, plus this Gaussian noise. We can write down the probability density of that vector v, which is, if hypothesis 0 occurs, namely if a 0 enters the communication channel, plus a is the signal which is chosen, then what happens is that the output is a plus z, which means that the probability density of the noise is v minus a. So we have this probability density here. When we look at the log likelihood ratio, we're taking the logarithm of this probability density divided by the probability density of the alternative hypothesis, namely v given 1, which is the same as this formula, except there's a plus a there instead of a minus a. So you get this thing here. Now, why I wanted to talk about this today is we're going to talk about the complex case also, and something very, very peculiar and funny happens there. Okay, so the log likelihood ratio is a scaled difference of the energy of the distance between v and a, which is this term here. This is just a squared distance between the vector v and the vector a. It's v minus a is that distance there, and squared. And the other term here is the term that comes from the probability density of v given 1, which turns out to be that distance there squared. So you have the difference between these two things. This is just the inner product of v minus a with v minus a. And if you multiply that all out, it's the inner product of v with itself plus the inner product of a with itself minus the inner product of v and a minus the inner product of a with v. The only things that don't cancel out between these two things is the inner product of v with a, the inner product of a with v, the inner product of v with a, the inner product of a with v. So those things last because there's a minus sign here and a plus sign here. There's a minus sign here and a plus sign here. So the plus and minus signs cancel out. So you just get 4 of these terms here, which is 4 times the inner product over n0. What happens to that geometrically? What is v, the inner product of v and a? Well, it's the projection of v on the vector a, which happens to be the line between minus a and plus a. Namely, the fact that it's a line between minus a and plus a is the thing which is valid whether you're dealing with antipodal communication or any other kind of communication. You're always looking at this line between 2 points. So what this thing says is you form the inner product, which says drop a perpendicular from v down to here, and in terms of where that perpendicular lands here, you make your decision. Namely, you compare that with the threshold. Okay, so we have 2 different ways of doing this. One of them is compare this distance with this distance, or actually here you compare the squared distance here with the squared distance there, which says if you're using maximum likelihood, then the threshold that you're dealing with here is 0, and you simply make your decision on whether the log likelihood ratio is positive or minus, which means in terms of the projection theorem here, what you're doing is taking a perpendicular bisector of the line between minus a and plus a and putting a plane there, and that's the plane that separates what goes into 1 and what goes into 0. This goes into 0, this goes into 1. Okay, so is it clear to all of you that this is really saying the same thing as this. This inner product just comes from here. You can either look at this as minimum distance decoding. You just find the point which is closest to what you receive. You find the hypothesized signal, which is closest to the actual observation that you make. You make your decision in terms of that. Or you do this projection and make your decision in terms of that. And if you use the triangle thing, which says that this squared distance plus this squared distance is equal to that squared distance, we all remember that from third grade or something. I don't know when. But that simply says the same thing that this says. This just says it more generally in terms of an arbitrary finite dimensional vector rather than just the case of where you're looking at 2 dimensions. Okay, we will probably come back to look at that in a little bit. But now I want to look at complex antipodal vectors in white Gaussian noise. So the setup there is that the input is some vector. I usually use u's to mean complex numbers. So the vector there is u1 up to u sub j, where u sub j is a complex number. So we're dealing with complex vectors at this point. So we have 2 points, minus a, minus u, and plus u, where instead of being a real vector, they're complex vectors. And if you can't visualize things geometrically in terms of complex vectors, join the crew. I can't either. The only thing I can ever do is talk about real vectors, try to get some idea of what's going on from that, and use mathematics for the complex vectors. Because the reason we use complex vectors is that analytically they're just as simple as real vectors. The reason we use real vectors is because we can draw pictures of them. And I defy anybody to draw a picture in 4 dimensions, although some books will do it, but I can't understand them. And anyway, okay, so under hypothesis 0, what gets sent is u, and under hypothesis 1, what gets sent is minus u. So we're still talking about binary communication. And if you're talking about antipodal vectors, you can't do much other than talk about binary communication. Because if you're sending a, the only vector antipodal to a is minus a, and then you're stuck and you're done. So we're still talking about binary vectors. Remember the reason why we're doing this. Because one of the things we did last time, one of the things that's in the notes and stressed again and again, is that once you understand the antipodal case, you can translate those 2 points anywhere you want to, and the maximum likelihood decision and the map decision are still the same thing. You take those 2 points and you just translate them in space until the mean between them sits on the 0 point, and then you're back to the antipodal case again. Okay, so the reason why we're doing this is really so we can look at the more general case, but we don't have to have that mean sitting around all the time. Okay, z then is going to be a vector of j complex IID Gaussian random variables, IID real and imaginary parts, namely the real part of each complex Gaussian random variable has variance n0/2, and the imaginary part also has variance n0/2. These complex vectors, if you look at the probability density for them and you draw it in 2 dimensions, one for the real part, one for the imaginary part, you get this circular symmetry that we've always associated. Those are supposed to be circles and not ellipses. And those are sometimes called proper complex Gaussian random variables, because almost everywhere where you see complex Gaussian random variables, the real and imaginary parts are independent of each other and both have the same variance. And again, when you look at formulas in papers, formulas everywhere else, they are almost always assuming this kind of circular symmetry, or what's often called proper complex random variables, sort of accepting the fact that anything else is very, very improper. It's improper because formulas don't work in that case. Okay, so we have a vector of these complex IID Gaussian random variables. Under h equals 0, the observation v is given by v equals u plus z. And under hypothesis 1, the observation is given by minus u plus z. So we have exactly the same cases we had before. Okay, in other words, almost all formulas stay the same when you go from real to complex. But I don't trust the complex case, and you shouldn't either, until you at least go through it once. So what I'm going to do now is translate this complex case to the real case. In other words, for each complex variable, I'm going to make two real variables, one the real part and one the imaginary part. And we know that the real part and the imaginary part are independent of each other. And if these Gaussian random variables are independent of each other, then the real and imaginary parts of each of them are independent of the real and imaginary parts of each of the others of them. Okay? So we can go from J Gaussian random variables, independent Gaussian random variables, which are complex, to 2J Gaussian random variables, which at this point are going to be real. Okay? So it's just a translation from J complex variables to 2J real variables. Again, we can't draw pictures of things in this J dimensions. We can start to draw pictures in 2J dimensions. If you talk about a probability density for a complex random variable, what are you talking about? How do you write the probability density for just a plain Gaussian complex random variable? What is it? Anybody know what it is? Is it one-dimensional or is it two-dimensional? What does probability density mean? It means probability per unit area. What does area mean when you're talking about complex numbers? Well, you sort of mean what you've drawn there, yes. And you're looking at areas in this complex plane here. So that in fact, when you write the probability density for a complex random variable, what you have already done, whether you want to do it or not, is you converted the problem to a real and imaginary part. That's what the probability densities are. Excuse me for belaboring this, but if I don't belabor it, I mean, there's a catch here that comes along in a little bit, and you won't understand the catch if you don't understand why these things are almost the same as real variables up until the catch comes. Okay, so we're going to deal with these 2J dimensional real vectors. The components will be real part of Uj, imaginary part of Uj for what goes into the channel, and we'll let capital Y and capital Z prime be the 2J dimensional real versions of V and Z. Okay, so that we'll call Y the real part and imaginary part of V. And you notice that what's going on here is the same thing that's going on when you modulate QAM. You take a complex signal, you multiply it by e to the 2 pi j carrier frequency times t, and then when we started to look at orthonormal expansions, you remember that what we looked at as far as the real signals that were actually being transmitted on the channel was the real part of that u of t times e to the blah, 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 an imaginary part of u of t times blah, blah, blah. So you got two orthonormal functions in place of one complex orthonormal function. And that's the same thing that's going on here. It's just not with the modulation put in. It's just with it's just dealing with the real parts and imaginary parts directly. Okay, so if we do that, we get a bunch of equations. They're sort of familiar looking equations by now, I hope. This is just the probability density of this real 2J dimensional random variable, which is all this junk that we're used to seeing. We can collapse that into e to the minus the norm squared of y minus a. This is the norm squared in this 2J dimensional real space. It's not the norm squared in this complex space. What gets confusing is that those two norms are exactly the same, as we'll see in just a few minutes. But anyway, what we're dealing with now is this norm in real space. Okay, note that y. Oh, let me translate this one for you. If we think of this v that we receive, j complex random variables, as being real part of v1, imaginary part of v1, real part of v2, imaginary part of v2, and so forth, then y 2j minus 1 minus a 2j minus 1. I can't ever get these formulas right. That should be a 2j minus 1 there. This squared plus this squared, okay, in other words, the real part squared of the difference plus the imaginary part squared of the difference is really just the same as vj minus uj squared. Okay, in other words, you take the complex number v sub j, you subtract off the real number u sub j, and the way to do that, you visualize this one complex variable in the complex plane, and what you're doing is you're taking the square of the real part of the distance, you're adding it to the square of the imaginary part of the distance. Okay, all of this is stuff you learned in high school, just viewed in a slightly different way. Okay, now when you take the probability density with respect to these complex vectors, which is what I want to get at, probability density of these complex variables really means the same thing as that with the real variables, but then you wind up with the magnitude of vj minus uj squared, and this term is really exactly the same as these two terms there. So when you take this probability density, you wind up with these terms the same and with these terms the same. Okay, in other words, the complex norm squared is the same as the real norm squared when you go from complex to real and imaginary parts of, well, as I said, this is the same as that. Okay, so when we look at the log likelihood ratio then, let's do the log likelihood ratio in terms of the real parts first. We get the difference between this norm squared of y minus a and the norm squared of y plus a. This is the part that comes from the hypothesis 0. This is the part that comes from the hypothesis 1. Okay, so we get these two terms here. When we take the inner products here, we get the same thing that we got before, 4 times the inner product of y and a. Now, the whole reason for going through all of this is this next formula. When you do this, you wind up with this very bizarre 4 times the real part of the inner product of v and u divided by n0. And you get it in exactly the same way that we got it before. Namely, you take this norm here, which is an inner product squared of v minus u. Let me write it out. I'll write it out here. Norm squared of y minus a is the norm squared of y plus the norm squared of a plus the inner product of minus y a plus the inner product of minus a y. What's the sum of these two inner products? This inner product, by definition, in terms of integrals, is the integral of minus y times a complex conjugate. This is minus a times y complex conjugate. So in one case, the complex conjugate is here. In the other case, it's on the other term. In other words, this and this are complex conjugates of each other. What happens when you add two complex conjugates? You get the real part of the two of them. Okay, so when you add these two things, you just get that real part there. Okay, and then when you do the other term, the same thing happens. The same cancellation that we had before occurs, and these two inner products add up. So you wind up with the real part of VU over N0. When we look at the picture here, what does it mean? Well, I suggest you first look at the one-dimensional case here. Namely, in this one-dimensional case, think of V as being a one-dimensional complex random variable. Then we can draw a picture. The picture makes sense, and what we're dealing with is the real and imaginary parts. And these distances here, when you talk about the norm of V minus A, namely what corresponds to this line here, the length of this line, what do you really mean by it? If you took the inner product, if you took the norm of V with I times A, namely the square root of minus 1 times A, would you get the same thing or wouldn't you? If I take a complex number and I take the inner product of that complex number, namely the product of that, when I take the inner product of YA, is this the same as the inner product of Y and I times A? Not at all. Two things are totally different. Namely, inner products are complex things. Norms are real things. And these norms, when you're dealing with complex numbers, have real parts in them. In other words, this distance that we're talking about here is not just the norm squared. Well, it is the norm squared because the norm has this complex feature built into it, because people kept making that mistake all the time. So they fudged the mathematics to make it come out right. But after doing that, you have to fudge the mathematics to come back to something that makes sense here. So you have the real part of this inner product here. So in fact, what you're doing when you're taking the inner product of two vectors and you're trying to relate it to this plane here, this separation plane, is you have to look at that separation plane. You have to look at that projection in terms of real numbers. Namely, you have to look at the projection first as being a complex projection of V onto A, which gives you a complex number. And then after you do that, you have to visualize yourself in a two-dimensional real space, and you have to project once more from the two-dimensional thing to the one-dimensional thing. And here, where we're just looking at one dimension to start with, we have to draw it as a two-dimensional space, and suddenly we are dealing with this real part there while we're not dealing with that here. Which is why when people say minimum distance detection, when they're dealing with complex numbers, it sounds very, very simple. But in fact, it's not so simple. Okay? If you view this in the complex plane, is this a linear operation or isn't it? When you're looking at things as complex vectors, is this thing a subspace of the complex vector space? No, it's not. It's not a subspace, because to be a subspace, you have to be able to multiply by arbitrary scalars, which include complex numbers, and stay in the same space. And here, the complex numbers are important. Okay? You should go back and think about that. You will be confused about it for the first 10 times you think about it. For those of you who stick with it and carry through on it, you will be happy because you'll never be confused about it again. But Okay, anyway, that real number is there. And the most straightforward way to deal with complex noise is to first turn it into real noise. If you do that, you never get confused. And otherwise, you only have half the analytical work, you only have half the writing to do, but you never know whether you've done the right thing until you go back and check. Okay, the probability of error for maximum likelihood detection, in other words, where the threshold for the log likelihood ratio is 0, is simply the same thing that it was before, namely it's the Q function, this tail of the Gaussian normal function of the norm of A divided by the square root of n0 over 2. In other words, it's the length of A divided by the length of a one standard deviation of this of the noise. When you put that in terms of, well, if you write this as the square root of the norm squared, then you get this formula here, because E sub B is just the energy of these antipodal signals. When you look at this in terms of the complex random variables, you get the same thing. Okay, you get U instead of A, because in fact in the complex plane and the real plane, distances turn out to be the same. But again, in all cases, it's square root of 2EB over n0. Now, that is true for any vector at all, where these norms are appropriate. When we start dealing with functions, what happens? When we start dealing with functions, what we're going to do is we're going to take this vector, we're going to turn it into a waveform, we're going to transmit the waveform is going to come back to us, we're going to demodulate it, get back to a number again, and that's the next thing that I want to talk about, because what I want to convince you of is the property of white Gaussian noise, which is so important, is that it doesn't make any difference how you modulate. All modulation systems are the same. All modulation schemes are the same. All frequencies are the same. There is no way you can avoid white Gaussian noise. There is no way you can get screwed by it. No matter what you do, the same thing happens. You can always take all these problems where you're dealing with waveforms, you can convert them to finite dimensional vector problems, and when you convert it to a finite dimensional vector problem, all of the orthonormal functions that you're using all pass away because none of them are relevant anymore. Okay, that's the bottom line of all of that. Okay, we haven't really talked about Emery hypothesis testing, so I want to talk about it a little bit now. I've talked about it just a shade, but not much. When we want to detect between m different hypotheses, namely in the vector case, we're going to now be detecting not between antipodal signals, but m signals which are placed any place at all. We already said what the optimal map test was. You see an observation, you're trying to guess what the input was or what the hypothesis was. And in general, the map test says try to find that J, namely that hypothesis, for which the a priori probability of hypothesis J times the likelihood, namely the probability that you see V given H of V given J, is maximum. Okay, this is just standard formula for finding a posteriori probabilities, where you factor out the marginal on when you cancel out the marginal on V. In other words, what this rule says is to do map testing. What you do is you find the a posteriori probabilities of each of the hypotheses, and you choose the a posteriori probability which is largest. Perfect common sense. The way we're going to do that, in the way which is particularly convenient, is you do it the same way that we've been doing all along for binary hypotheses. The way to do a map test, or at least one way to do a map test, is you compare every pair of hypotheses and you choose the most likely of each pair. And when you get all done, you have a winner. Okay? Namely, you can always compare any objects if they're comparable. And after you compare each pair, you take the one which beats every other one, and that's the winner. Okay, so what you do is you do a pairwise test between each hypothesis, namely the likelihood ratio of m relative to m prime is the likelihood of the output conditional on m divided by the likelihood of the output conditional on m prime. You compare it with the a priori probabilities, and the point here is that nothing really has been added. You have the same problem you had before, okay? Nothing new. It's just got an m squared times as complicated. But computation is free now. So you have exactly the same problem that you had before. If you have to write it out on paper, yeah, it's much more complicated. But conceptually, it's not. You have to remember that the signals are not antipodal here. But what we're dealing with mostly at this point is this Gaussian noise case. And here what you observe is signal plus noise. And Z is zero mean jointly Gauss. And S is discrete with m possible values. Okay, so let's see what that means. Here's a picture of it. If you have three signals which are each two-dimensional vectors, suppose one of them is S0, suppose one of them is S1, suppose one of them is S2. Okay, and now you want to pairwise see which one is most likely. And let's think of doing this first for the maximum likelihood case. What do? You set up a perpendicular bisector between S0 and S1. That's this line here. And if you weren't to worry about S2, everything on this side would go into H0, H equals 0, and everything on this side would go into H equals 1. Namely, whatever is closest to this point gets mapped into it. Whatever is closest to this point gets mapped into it. If you're doing map testing, what happens? In the test between this and this, you have the same orientation for this line, but it just gets shifted a little bit this way or a little bit this way. Okay, then you compare this with this, and you get this line here. Same argument as before. It's just comparing two things that are not antipodal. They've just been shifted off from the origin a little bit. But for maximum likelihood, you still take the perpendicular bisector between them. And then you compare these two, and you got a perpendicular bisector between those. And these perpendicular bisectors in two dimensions always come together at one point. And I don't know why. And if you looked at it often enough, you probably know why, and you could probably prove it in about 10 minutes. But in fact, these things always come together somehow. If you do the map test, they always come together also. You can shift each of them in arbitrary ways, and somehow they always come together in this point. Okay, the separators between decision regions here are the set of points where the real part of the inner product, VU, is constant. Okay, again, for dealing with complex vectors, you got to both do the projection and then do the projection again onto the real part of this projection. So it's a sort of a two-way projection. Because probability densities in j-dimensional complex space are really two j-dimensional quantities. And when you're comparing them, you really have to compare things in terms of that two j-dimensional probability density. Okay, so that's why that comes out. These are best visualized in separate real and imaginary coordinates. And for maximum likelihood detection, the regions are Voronoi regions. Okay, we talked about Voronoi regions in terms of in terms of doing quantization, and we found out if you wanted to minimize mean square error, what you did was you set up regions which are perpendicular bisectors between all the points. And here you get the same perpendicular bisectors between the points. And everybody, because of that, thinks that quantization has a great deal to do with error probability when you have large sets of signals. And it probably has something to do with it, but I don't know what, other than the fact that you got Voronoi regions in each case, which is what you get. Okay, so that's where we are with both complex vectors and real vectors. I want to now just restrict attention to real waveforms so I don't have to keep going back and forth between the real and imaginary case. If you're thinking in terms of QAM, we're now thinking in terms of what goes on at passband. Why do we want to think of what goes on at passband? Because that's where the noise hits us. And in a fundamental sense, all of the stuff about QAM really isn't fundamental. I mean, it's all done, all this stuff down at passband is all done because people thought it was easier to implement things there. It's the only reason for all of that mess with dealing with all of these complex signals. If we really want to deal with the problem in a fundamental way, what we want to do is to choose a signal set up at passband, do detection up at passband, and then after we find out what the optimal detection is up at passband, see if we can actually implement that down at baseband. So the fundamental problem is look at signal sets up at passband, analyze what they all mean. Okay, so we're going to generalize both PAM and QAM, and now we're going to look at the general problem where what we're dealing with is a signal set which is M signals. Each of them we're going to visualize as a vector in j-dimensional space. M different signals, j-dimensional space. Don't confuse the dimension of the space with the number of signals. Okay, you can have an arbitrarily large dimensional space and just binary signals, or you can have an arbitrarily large set of signals and you can be dealing with it. MPAM, for example, is just all done in one dimension. So j there is equal to 1. QAM, j is equal to 2. We now want to look at more general things. Partly because we want to look at orthogonal waveforms. We want to look at orthogonal waveforms for two reasons. One is that we would like to show that by using orthogonal waveforms, you can reach what we've called the capacity of a white Gaussian noise channel. And two, when we get to studying wireless, it's very, very useful to base signal sets on orthonormal sets of functions. And we'll see why each of those things happen as we move on. Okay, so we're going to denote the signal set as the set of vectors A1 up to A sub m. And in that signal set, we will denote the vector A sub m as a j-dimensional vector, A sub m1, A sub m2, up to A sub m capital J. So j is a dimension, m is just the components of these vectors. I'm going to create a set of capital J orthonormal waveforms. They can be anything at all. I don't care what they are. I'm going to use those orthonormal waveforms in order to modulate the signal, which is now a vector, up to some waveform. You know, this is really the standard way we've been turning signals into waveforms all along. It's just that now we're looking at the general case instead of all of these specific cases that we've been looking at. All of the special cases all fit into this same category. So we have these capital M different waveforms, and we're going to transmit one of them, and then at the receiver we're going to try to decide which one was sent. Okay, well, one of the reasons why I'm going through all of this generality is there's there's an issue we haven't talked about yet. All of the stuff we've done on detection so far, we have had one hypothesis. Could be emery, could be binary. We have sent something, we have received something, we've made a detection. Okay, in other words, for all of the antipodal stuff we've done, we've built a communication system, we've set it all up, we've transmitted one bit, we've received the one bit, we've made a decision on it, then we've torn down the communication system and we've gone home. You really want to transmit a whole sequence of symbols or signals or waveforms. So we want to deal with that now. So we need some way to transmit a succession of emery signals. And we'll call this succession of signals, namely the signals are the things that get chosen from the signal set. We'll call them x sub k, k, and z, which is what we've been calling them all along. We've been transmitting a sequence of things when we're dealing with PAM and AA and AM. Why do I call them xk instead of AK? Well, I can't call them AK because when I talk about AK, I'm talking about the kth signal in the signal set. And here what I'm talking about now is transmitting a sequence of choices. Each one of these choices, the first choice is a choice from this set here. The second thing that I send is a choice from this set. The third thing that I send is a choice from this set. So x1, x2, x3, x4, and so forth are different choices among these emery signals. If m is 2 to the 6th, okay, in other words, every time I transmit a signal, I'm transmitting 6 bits. Okay, in a communication system, we transmit 6 bits, then we transmit another 6 bits, then we transmit another 6 bits, and so on forever. Okay, so I need to talk about these things as ways of a succession of signals. The thing that I'm trying to get at is how do you know when you send one of these signals that you don't have to worry about the other signals? How do you know that they don't interfere with each other? Will we sort of solve the problem of them interfering with each other in dealing with Nyquist? But we haven't dealt with that problem at all since we started to talk about random processes. So we don't know whether we've really solved it or not. So at this point, we have to solve that problem. And that's what we're aiming at. So that one way to be able to transmit a whole sequence of signals is to have these choices of vectors here and to develop a set of orthonormal waveforms, phi1 up to phi sub j, which all have the property that if you time shift them each by capital T, they're still, if you time shift them by capital T, they have to be orthonormal to each other. The question you're facing is whether these things that you're transmitting are orthogonal to all of these things that you're transmitting. Now, in the Nyquist problem, we dealt with the problem of how do you take one waveform here and make it orthonormal to all of its time shifts, and we solved that problem. In the quiz, you solved the problem, although you probably didn't recognize it, of dealing with orthonormal functions both in time and in frequency, and that's the kind of thing we would like to use here. If I take a set of orthonormal pulses and then I modulate those orthonormal pulses up to a higher frequency, which is out of the range of this first frequency, then I can send one sequence of orthonormal functions down here, another set of orthonormal functions up here in a different frequency range, another one up here in a different frequency range, and so forth. So then all of these orthonormal functions are going to be orthonormal to each other. Yeah?
Are you saying, is this a degree?
What?
Or is this a degree of freedom unit? Are you saying that each x of k gets its own frequency? Each x of k is like infinitely long.
Each x of k is going to, each x of k is just a vector of j components. I'm going to modulate that vector x of k into a waveform x of t, which might be finite duration or it might be infinite duration. I mean, it's going to go to 0 very, very fast anyway. And whether it is absolutely time limited or not is something I don't really care about at this point. But the point is I can create functions where in fact I have a whole sequence of functions here and they're orthonormal to all of their shifts. One way of doing this, for example, is to make capital J a bunch of little time shifts on functions. I can pick a function p of t, which is orthonormal to all of its shifts in terms of t1. I can send j of those pulses to take care of x sub k, and then I can use a capital T in here, which is j times this little t that I was using, and I can send another set of functions. So I can do that. I can move up and down in frequency. I can choose any old set of orthonormal functions that I want to. But the thing that I want to do is I want to make sure that for each vector x sub k that I'm sending in time, when I modulate it to a waveform, that waveform is orthonormal to the waveforms for every other k. And there are lots of ways of doing that. Okay? Mainly, there are lots of choices of orthonormal functions. Okay, so anyway, what I'm going to be doing is making all of these signals orthogonal to each other. Okay, so the transmitted waveform for this sequence of modulated signals is x of t, which is a sum of x sub k times t minus kt. Namely, the same thing we were doing before, except now I have also the problem that each of these waveforms x sub k of t has to be some sum of orthonormal functions. So the problem becomes a little more difficult than what it was before. But in fact, this is just standard communication. Every wireless system in the world uses this kind of scheme. They don't use QAM or PAM. They use something much more like this. Okay, so now our problem is you want to detect a generic x from this sequence. Okay, in other words, one of these x sub k's in sequence, we want to be able to detect what signal was sent. We want to detect which hypothesis chose a signal which was then formed into a waveform x sub k of t. And if I can do this for 1k, I can do it for all of them. So I want to solve the problem for one generic value of k. Okay, how is this problem different from what I was looking at before? Before, I was looking at the problem where we built a communication system, we tuned it all up, we sent one bit, we detected it, we tore it all down, and we went home. Now what we're doing is we're building the communication system, we're tuning it all up, we're sending a sequence of bits, and then all I'm interested in at the moment is detecting the kth of them. But if I find a way to detect the kth of them, I can then use it for every k. Okay, so I'm going to build a detector which is going to detect in some optimal way each one of these signals that gets sent. Okay, is it clear how the problem is different? Namely, I have to deal with the fact that these other signals are floating around there. And that's my problem. Okay, so the input to the channel is hypothesis H. That takes values 1 up to m. The symbol m is mapped into the signal vector a sub m. It's modulated into x of t equals summation over j, a sub mj, phi j of t. Okay, this waveform now is a function of which particular signal I'm sending, which is a function of which particular hypothesis entered the encoder. The trouble with this material is all the complication comes in this awful notation, which you can't avoid, because you're dealing with sequences, you're dealing with vectors, and you're dealing with waveforms all at the same time. What's going on after you understand it, you will say, why was it so difficult to understand this? Because eventually when you see it, it becomes very, very simple. And I understand why there's just too much stuff all going on at the same time. Okay, so what I'm going to do now is I'm going to take these capital J, orthonormal waveforms, and we've already seen that you can start out with any old orthonormal waveforms, and if you want to, you can extend that set of waveforms into an orthonormal set that spans all of L2. Okay, so I'm going to imagine that we've done that. It's taken us a long time, but we've done it. We're all through with it. We have this orthonormal set now. If I'm smart, that orthonormal set, which I've generated, will also include easy ways to represent each of the other signals that we're going to send. But I don't care about that right now. All I'm dealing with is this one hypothesis that came in, this one signal A sub k, A sub m, the hypothesis m, the signal A sub m, and a particular time instant k, and this waveform that gets sent, which can be represented as the first j terms in this orthonormal sequence. Okay, so what I'm going to get then is the received random process is going to be some, and forget about the j prime now. I can represent it as a sum of coefficients times these orthonormal waveforms. Okay, that's what we've done for arbitrary sequences, and then we've said we can also do it for at least well-defined random processes. I'm going to make, instead of making this an infinite dimensional sum, I want to make it a finite dimensional sum where j prime is very, very large. Say 10 to the 50th if you want to. But I don't want to make it infinite. I want to look at what happens when I let it get bigger or smaller. So I'm expanding y of t over an orthonormal expansion, but I'm not going all the way. I'm just going to try to do maximum likelihood detection with this finite set of observations. So I won't do quite as well as if I have all the observations, but I'll still do pretty well, we hope. Okay, so y sub j, the output that I see in this degree of freedom corresponding to phi sub j of t is going to be xj, what I sent in that degree of freedom, plus zj. And there are capital J degrees of freedom that I'm using, so the outputs in those degrees of freedom, namely in the phi 1 of t, phi 2 of t, phi 3 of t directions in this L2 space, are going to be the signal plus the noise for all of these dimensions. And yj is just going to be equal to zj for all the other terms. Okay, now I want to add one extra thing here. What I should be putting in here is all the other signals that are going to be transmitted. And I don't know how to do that. Notationally, it gets very confusing. So what I'm going to say is, okay, z sub j here is not just Gaussian noise. Z sub j is Gaussian noise plus all the signals from other time instants that we're sending, plus all of the signals that anybody else is sending if we're dealing with wireless and we have interference from them, plus any old other thing you can think of. Z sub j is everything, but in these other degrees of freedom, in these other coordinates. This solves another problem for us, because when we defined white Gaussian noise, we had this problem that we could only say it looked white over the region of interest. We could only say it looked white over some time span, because the Earth keeps changing, you know, and over some frequency span, because different frequencies behave in different ways. So this also allows us to have different Gaussian random variables here. So we have arbitrary random variables here. They can be Gaussian or non-Gaussian. They don't have to have the same variance. They don't have to have anything. What I am going to assume is that these out-of-band, out-of-sense, out-of-view random variables are all independent of the things that I am looking at. And for white Gaussian noise, that's true. All of these random variables here are independent of all of these random variables here for these first capital J different random variables that I'm interested in. And all of these random variables are independent of the input that I'm using. Okay, in other words, the hypothesis came into the transmitter that generated a signal. The signal got turned into a waveform which is defined solely in terms of these J degrees of freedom, these J orthonormal functions. And now everything everywhere else is independent of these J functions that I'm interested in. Why is that a shaky assumption? Can anybody think of a situation where that is absolute nonsense? Yeah.
The stuff from the other next to J, like at T, is going to. You said ZJ is not just Gaussian. It's not just the white Gaussian noise. It's also the.
Also includes all those other signals. Yes. Yes. Well, but I want to assume that those other signals are independent of this particular signal that I'm sending. But in fact, that is making a pretty big assumption. Because one of the things that a lot of people like to do is when these bits come into a channel, the first thing they do is they encode the bits for error correction. And then they take those bits that come out of the error correction device, error encoding device, which are as correlated as could be. And they're all statistically very dependent because we want to use that statistical dependence later to correct errors. And this assumption that I'm making here says, no, that's not the case. I'm assuming that all that other stuff is independent of what I'm transmitting here. So I'm very specifically assuming at this point that all of that stuff has not been encoded first, that I'm sending something which is independent of everything else which is going to enter this channel. Okay? We'll just assume that, and after we get done assuming it and seeing what the consequence of it is, we'll go back and see what it all means. Okay, for a little more notation, I'm going to call the vector y the first J, capital J outputs. I'm going to call the vector y prime all the other outputs. Now, intuitively, what we're aiming at is we would like to say this stuff doesn't have anything to do with it. We're going to base our decision on this. But I want to prove that to you and show you why it works and why it doesn't. And the noise I'm going to break up the same way. Z is the first J components of the noise, and Z prime is the other components of the noise. So what I have is that the output that I want to look at, namely the output, this vector of dimension J output, which is equal to a vector of dimension J input plus a vector of dimension J noise, is equal to, well, y is equal to x plus z, and the out-of-band stuff, the output, is just these noise and other signals, okay? And I want to assume that z prime, x, and z are statistically independent. Question, test your probability. If I assume that z prime is independent of z, and if I assume that z prime is independent of x, does that mean that z prime is independent of x and z? If A is independent of B and A is independent of C, is A necessarily independent of the pair BC? How many think that's true? Better go back and study study a little elementary probability again. And the notes are occasionally wrong about that too, so you shouldn't feel badly about it. No, the problem is you really need this joint independence between all three of them. I could, for example, make x plus y be equal to z. I could do this with discrete random variables, which are equally probably 0 and 1, and make the plus equal to a mod 2 operation. And if I did that, each pair would be independent of each other, and the triple would be very, very highly dependent. So anyway, I want to assume that z prime, x, and z are statistically independent. In other words, what I'm doing is saying, if I assume that, what's the consequence of it? Okay, so the likelihood then, the probability density of the output y, this is the output in the first j dimensions, given a particular hypothesis y, is equal to the probability density of the noise evaluated at y minus am, where this is the signal that goes with this hypothesis, well, with m, times the probability density of y prime for z prime. Okay, and I don't even have to assume that this is Gaussian. All I've done is to assume that these random variables are independent of these random variables, and therefore this probability density is multiplied by this probability density. Okay, well that's kind of neat, because if I put a different I in here in place of m, I get this thing changes all around, f sub z of y minus a sub I. But this stuff, which is out of band, doesn't change at all. When I form the likelihood ratio, what I get then is this divided by that. What has happened to y prime? Y prime has disappeared. In other words, y1 to y sub j are a sufficient statistic for this problem. We have shown that sufficient statistics are the only thing you need to use to do maximum likelihood detection. Okay, in other words, all those other signals, all that other noise, all that stuff from out of band has disappeared. Now let's go back to the fact that we were looking at a finite dimensional problem. What happens now when I make j prime bigger, when I start enlarging j prime? What happens to all these probabilities that we're talking about? This probability density goes ape because of this term here. We're talking about a probability density here which is involving more and more and more terms. I can't talk about that. It doesn't go to any limit. It goes to absolute nonsense as j prime gets big. But if I form the likelihood ratio before I go to the limit, then I can go to the limit quite easily because there isn't any limit involved there. Okay, in other words, this is the likelihood ratio between hypothesis M and hypothesis I, if in fact I looked at this entire infinite amount of observation. This is all I need to make the optimal map decision. Okay, so there's a theorem here which is called the Theorem of Irrelevance. This is something that Wozencraft and Jacobs, in their book on communication many years ago, stressed a lot in trying to come up with a signal space viewpoint of communication. And you'll see why this really does give you a signal point viewpoint of communication. It says that assume that z prime is statistically independent of the pair x and z. Then the map detection of x from the observation of y and y prime depends only on y. The observed sample value of y prime is irrelevant. Okay, so you can do all of detection theory, you can do all of communication, simply forgetting about that irrelevant stuff. Because of the theorem, we can stick to finite dimensional vectors, and the other signals can be viewed as part of z prime. So you don't have to worry about them. So long as each signal is independent of each other, which means that these groups of bits, the first group of bits is used to form a sub x sub 1, the next group to form x sub 2, the next group to form x sub 3, and so forth. So long as those sequences of bits are independent of each other, you're fine. Now, suppose they aren't. What happens then? Interesting question. we said that if they are independent, I can really do maximum likelihood detection on the whole sequence. If they aren't independent, suppose I say, well, I don't care about that. I'm just going to use this portion of the output to make my decision and not worry about whether this is independent of anything else. I can do that. This still is going to give me the optimal maximum likelihood detection in terms of the observation y1 up to y sub j. So in other words, whether I have coding done before this or not doesn't make any difference. I can still use maximum likelihood detection on the basis of y1 up to y sub j. What the theorem says is if this out-of-band stuff, both the inputs and the noise, are independent of what I'm trying to detect, maximum likelihood becomes the optimum thing to do for equally likely inputs. And otherwise, it's a perfectly reasonable thing to do, but it's not optimal. Now, a lot of people, and we'll see some examples of this when we look at wireless, in fact, use coding, then they use this particular kind of detection where they forget about all of the added information from other signals. They make a decision on each of these x sub k's, namely each of the m-ary signals that goes in, they make a hard decision on it. It's called a hard decision, not because it's difficult, but because they refuse to ever go back and change it. If they just save likelihoods and try to put things together in the final decoder, it's called soft decoding. Otherwise, it's called hard decoding. If you do soft decoding, it has to work better because you're making, in a sense, a better decision because eventually you're using more information. So soft decisions are better than hard decisions. Used to be that everybody used hard decisions because hard decisions were easy and soft decisions were hard. Strange, strange thing. But anyway, that's changed. Why? Well, it ought to be obvious why, because anything you build now costs a tenth of what it used to cost to build it. Heard Erwin Jacobs a while ago saying that one of the things that they always did when they were designing new pieces of equipment is they would look at how much it would cost to build these devices, and then as opposed to most companies which would say that's too expensive, let's find a cheaper way to do it, they said, okay, how long is it going to take for us to do it, and what is the price of components going to be by the time we get it done? And they would usually say, well, it's going to cost a year before we can go into mass production, and by that time everything will cost less than a half of what it's costing now, so let's go ahead and do it the right way. So again, the argument comes that you can do the hard thing now, which is soft decisions, and that's what most people do at this point. Let me give you one more picture to get ready for what we're doing next time, because it's a nice picture of different signal sets, because we've just talked abstractly of having multiple signals viewed as vectors, and this will give us some idea of what all of these mean. I can have two signals, a binary signal set, and I can insist on the signals being orthogonal to each other, which is a nice thing to do sometimes. But then I can look at it and I can say, how can I make that a better signal system? The trouble with this signal system is it's not antipodal. It's not antipodal because somehow by alternating between these two orthogonal signals, there's a mean between them, and I'm transmitting that mean plus the difference. And the difference between them is minus 0.7 and plus 0.7 in that direction that way. If you can, I guess you can't see it that way. In this direction, this way. Well, anyway. Okay. Better thing to do than this is this, which is called biorthogonal. So So you take orthogonal signals, and then you have a signal set consisting of 4 signals in 2-dimensional space. We can talk about orthogonal signals in higher dimensional space. You can talk about 3 orthogonal signals in 3-dimensional space here, there, and there. So that's m equals 3 and j equals 3. If you do the same thing that we did here, we're going to make this into an equilateral triangle. Namely, we're going to center it around the center. If we do the same thing that we did here, we're going to turn this into a set of 6 waveforms, which are still using the 3 degrees of freedom, but at least get us more signals for the same number of degrees of freedom. So you can extend this picture as far as you want to. You can talk about many, many orthogonal signals going into many more degrees of freedom. For each one of them, you can come up with a simplex set of signals. The nice thing about the simplex set of signals is that all the signals are arranged around the center point. They're all equally distant from each other. You can get these for every dimension by starting with these and simply taking the mean out, which loses you 1 dimension and makes this sort of ideal set. Well, tomorrow, on Wednesday, what we're going to do is we're going to talk about these large sets here and see what happens. And we'll see that you, in fact, get the channel capacity this way. Okay.